The second law is the law of acceleration. Oops. And that law, well, Isaac Newton described it in this way, that the acceleration is equal to the force divided by the mass, that the acceleration, let's talk about proportionalities or relationships. The acceleration is directly proportional to the force. That is, if the force goes up, the acceleration will go up. And acceleration is inversely proportional to the mass. That is, if the mass goes up, the acceleration will go down. We'll talk about throughout this course these mathematical relationships, and I'll use this symbol, which is the Greek letter alpha, and it just simply means that a variable is proportional to another variable. That is, it's proportional to in the sense that if that variable changes, in this case f or m, then the other variable also changes. In that case, it's a. More commonly, you see Newton's second law as F equals ma, and I think this is how I give it to you on the equation sheet. Before we move on, I want to just go over some definitions which are important. The first is the net force. The net force, when we're talking about forces, we need to understand that forces are vectors, and the net force is the vector sum of all forces. So let's say, for example, I have an object. This is a block. We use blocks a lot in physics. I don't know. They're easy to draw, and none of us are very good artists. If I have a force and I have a block and I have two forces acting on it. Say that I have one force that has a value of 2 newtons. By the way, the unit of force is the newton. 1 newton. It's abbreviated 1 capital N. Whenever we have units that are named after people's names, the first letter, if it's spelled out, is lowercase, but if it's after a person's name, it's going to be capitalized when we abbreviate it. You'll see that with other units that we have. The basic SI units of this are kilogram meter per second squared. So 1 newton is equal to 1 kilogram meter per second squared. I can look at the equation. I know that M is in kilograms and A is in meters per second squared. So sometimes on the exam I'll ask you, or on the quiz I'll ask you, what are the basic SI units that make up a newton, for example? And it's going to be a kilogram meter per second squared. Also, just keep in mind a newton is about a quarter pound. Is about 1/4 pound, which, I think that if you really love this course, that next time you go to McDonald's, that you should, instead of going up to the counter and asking for a 1/4 pounder, that you should instead ask the person at the counter, with great respect and thankfulness for them doing their job, but ask them, say, hey, can I have a Newton burger? And they'll say, what? And you'll say, I want a Newton burger. And they'll say, what? It's like, oh, I'm sorry, you're in the British system. I'll take a 1/4 pounder or a 1/4 pound burger. So I don't know, you can try that if you want, see what they say. If you do that, let me know, because I'd love to hear about it. So let's return to our block over here. I have a 2 Newton force to the right, and then I also have a 3 Newton force. Now, if I put those two forces together, they will have a net vector. That will be 2 plus 3 equal to 5. However, if I have a similar block, and I have, say, a 3 Newton force in this direction and a 2 Newton force in this direction, in this case, the sum of those forces would be 3 newtons minus 2 newtons, and that's equal to 1 newton. The reason that we have this negative is because I'm in a right-handed coordinate system, and you can have a left-handed coordinate system, but we always use a right-handed coordinate system. This is the positive x direction, this is the negative x, this is the plus y, and this is the negative y. There is a plus and minus z, but we're not worried about that right now. So we typically take left to be negative, much to the chagrin of many left-handed people in the world, and I can think of many left-handed people that are, I don't know, contributed to society in a variety of ways. I think Isaac Newton was left-handed. I think John Grisham, the famous author, he's left-handed. And yours truly is also left-handed. But we bear a burden in the society because we are very much opposed to left-handed people. But I digress. So when we have a force to the left or in the downward directions, and we take that as negative. By the way, let's talk about free body diagrams. Free body diagrams, I think your book actually talks about this. A free body diagram is something that we've already done. This is an FBD, or a free body diagram. Free body diagrams are simply drawing a picture of the object with all the forces that are acting upon it. So for example, if I think about all the forces that are acting on me right now, that's a picture of me in case you didn't see. I have a couple of forces acting on me. I have the force due to weight that's acting down. I have a certain weight that comes about because of the gravity that's on the Earth. We'll talk about that later. I also have another force, which I call the normal force. Not just me, other people call it that too. And then let's say, for example, that you're pulling on me. You have a rope attached to me, attached to my waist, and you're pulling on me to the left, but I'm not moving because I'm pushing back. And so I would have, say, another force. I'm going to call that F me. What I've done there is I've drawn a free body diagram. Further, forces are vectors, and let's say that I have a force that is not upon the x or y axis. I can break this force into two different components, and those components are going to lie in the x, fx, and the fy in the y directions. The components of vectors are kind of like shadows of that vector. You can think about this vector is casting a shadow on the y-axis, and it's also casting a shadow on the x-axis. And notice here that the tips of the vectors will meet as I project them onto the x or y-axes. You can think about this better if you, I don't know, if you think about, I have a rope, and I have a guy that's pulling on the rope right here. I could replace that guy with two other guys that are pulling in this direction. So if I replace that guy with two other guys that are pulling in these x and y directions, it could still cause the same force acting at this point. That's the component. Those are the components of the force, just parts of that force that are on the x and y directions. Acceleration and velocity. Velocity is a change in position over time. Velocity then is equal to delta x over delta t, and acceleration is a change in velocity over time. I'm just going to write the equation. It's going to be delta v over delta t. Now, velocity will have units of meters per second, and acceleration asks how quickly does the velocity change will be meters per second. Meters for every second, I change by a meter per second, or meters per second squared. Those would be the same. I'll have a video for you, a couple of different videos, but I have a video about the acceleration due to the Earth's gravitational field. And the acceleration due to the Earth is going to be equal to minus 10 meters per second squared. This is due to the Earth. We'll see that comes up a little bit later when we're calculating the weight of an object, but the acceleration as an object falls through Earth's gravitational field, let's have a little more space here. As an object falls and goes down towards the ground, it accelerates at this rate of minus 10 meters per second squared. That means for every second that passes, the speed of that object increases by 10 meters per second. So say here is t equal 1. Now the speed is going to be minus 10 meters per second, or the velocity will be minus 10 meters per second. At t equal 2, it will be minus 20 meters per second. At t equals 3, minus 30 meters per second, and on and on. For every second of an object accelerating at minus 10 meters per second squared, it's going to increase its speed by 10 meters per second. And the negative here will denote the direction in the negative y direction. We'll talk more about that as we move into the different types of forces.